Hi everyone. Explain about multiple frequency CW radar. So in the previous videos when I have explained the CW radar, I told you about the CW radar which can be used to measure only velocity. Okay. So if you see the different types of radar systems, we have seen pulse radar. Why I am saying the different types of radar system in every video, you should know the difference between radar to radar. When you are moving from one radar to another radar, what is the difference and what is the new feature that has been added when compared to the previous radar? You should know. So in the pulsar radar, we have seen pulsar radar is used to measure the range. It cannot calculate the velocity. Okay, you should know these differences. And CW radar is used to calculate velocity using Doppler frequency, but not the range. CW radar cannot calculate range. And FM CW radar, we have also CW radar. FM CW radar is used to find both range and as well as velocity. Okay, this is what we have seen so far in the previous videos. Okay, so pulse radar can only measure range. CW radar can measure FMC. So FMCW radar is the next level of radar system compared to pulse radar and CW radar, which is used to measure both the parameters like range and velocity. That is the advantage of FMCW radar compared to pulse radar and the CW radar. Now, in this concept, I am going to introduce a multiple frequency CW radar that can also be used to find the range. Okay, so here I am going to explain a topic, a radar system called multiple frequency CW radar, multiple frequency CW radar that can also calculate CW radar can be used to calculate the velocity. Along with that, if instead of single frequency, how many frequencies we have transmitted using the CW radar system? Only one frequency. Now instead of single frequency, if we are using multiple frequency, let us consider two frequencies from the same transmitting section, okay, like F1 and F2. With such different frequencies, we can get the range parameter by taking the time gap between transmitted and received signals. Okay, so here the problem of CW radar is not considering the time gap between the transmitter and received signals. So if we take the time gap between transmitter and received signals, T is nothing but what do you mean by C? What do you mean by T? C, what is this? R by 2R by C. Okay, already we know R is equal to CTR by 2, CT by 2. So we can write T is equal to 2R by C. So if we know this time gap between the transmitter and receiver signals, the same method we have used for the FMCW radar. Here also in the multiple frequency CW radar, we are going to use the same technique taking the time gap between the transmitted and received signals with two different frequencies. Then we can also achieve the parameter called range. That is the advantage of multiple frequency CW radar. That means the drawback in the standard CW radar can be avoided by using multiple frequency CW radar. That is nothing but range measurement. The drawback is nothing but range measurement. The standard CW radar cannot calculate range, but multiple CW radar can calculate range. Okay. Now let us consider a CW radar with two frequency transmissions. Okay, that means we are taking two different frequencies from the same transmitting section. So what is the normal CW radar transmitter, CW radar transmitter, and the output of this one in the receiver section, mixer and amplifier, beat frequency amplifier, and then output. So instead of transmitting a single frequency like F0, we are transmitting now two different frequencies F1 and F2. So they will be F1 comma F2. So the transmitted signals are, let us consider the transmitted equal to V1 is equal to, V1 is the first signal that we are transmitting. V1 is equal to sine. So to know the difference, let us consider V1t sine 2 pi f1t less some. Okay, so 2 pi f1t plus phi 1, where phi 1 is nothing but some arbitrary constant. And second signal we are transmitting with a different frequency f2, yes, sine 2 pi f2t plus phi 2. Okay, here it is the bracket. So these are the two different frequencies we are taking with the two different signals like sine 2 pi f1t and sine 2 pi f2t. Where what about the phi 1 and phi 2? Where phi 1 and phi 2 are arbitrary constants. Okay, phi 1 phi 2 are nothing but arbitrary constant. However, they can cancel later, no problem. You can keep or you can easily discard them. Now after some time let us consider t. After some time t, how can you write the t is equal to object. Let us consider the object is at a distance r or r naught. So 2 r naught by c, where r naught is, what is r naught? The distance between, let us assume r naught is the distance between target and radar system. Okay, now after some time t, the received signals are, the received signals, how many signals we are receiving? Two signals. For v1t, one signal will be coming back. For v2t, another signal will be coming back. So we can receive those signals as v1r. v1r is corresponding to v1t, received signal for the first transmitted signal. v1r is equal to sine, see carefully, 2 pi, the first transmitted signal frequency f1 has to be added or subtracted with the Doppler frequency component, because if the target is in motion, some Doppler frequency component will be added or subtracted depending upon the movement of the object. Okay, so definitely f1 plus or minus fd will come. So f1 plus or minus fd, that is for the first signal fd1 into t minus 4 pi. See here what happens. 2 pi f1t. 2 pi f1t. When we are receiving the signal back after some time, 2 pi f1t minus t. That is the actual difference between the times we are going to see. I will explain here. 4 pi r naught into f1 by c plus some arbitrary constant phi 1. See what is happening, how this parameter has come, I am explaining. Normally the signal will be received after some time. So 2 pi f1 t minus t. Along with this Doppler frequency shift in terms of frequency, time is also shifted. That means we are receiving the same signal after some time. So 2 pi f1 t. So 2 pi f1 t, now we can write 2 pi f1 capital T. This t will come in the first parameter. So 2 pi f1 into capital T. So t is nothing but 2r by c. I already told you. So 2 pi f1 to r. R is nothing but r naught we have taken, 2 r naught by c. So then it is 4 pi r naught f1 by c. In this way we have got this parameter because of the delay. Similarly, the second parameter we can write it as 2r signal, received signal for the second transmitted signal, sine 2 pi f1 plus or minus fd2 for the second, sorry, it is f2, f2 fd2 t minus what happens, same parameter 4 pi r naught, it is f2 by c plus f2, so phi 2. Okay. Now, how many targets we are taking? Only one target. For one particular target, when we are transmitting signal from the same radar system, because the position of the radar system is same for both the targets. Sorry, for one target. See here, one target I am assuming. One target I am assuming. Let us consider this is the object which is in movement. Okay. Now a different frequencies are being transmitted from the CW radar like F1 and F2. For F1, one Doppler frequency will come. For F2, another Doppler frequency will come. But in general, as the object is same and as the radar system is same, but we are transmitting different frequencies, the Doppler frequency FD is same for both the frequencies F1 and F2 because the radar system is same, object is same. Suppose if the object is different, then it will be receiving two different Doppler frequencies. But as the object is common for both the frequencies, then we will be having only one Doppler frequency shift. So as there is only one target F F F F F F F F F F fd1 is equal to fd2 is equal to simply let us consider fd. Okay, so this is because of the single radar system and the single target. Then see here, fd1 is equal to fd2. Okay, no problem. Now this is the received signal and this is the received signal. When this received signal f1 v1r is transmitted through a mixer, what is the purpose of mixer? The received signal and the transmitted signal from this side V1T. These two are subtracted to each other. That means the detector will detect what is the resultant signal after the mixing. That means what is the purpose of detector? Detector will eliminate the transmitted frequency component. So when the received signal and transmitted signal passing through detector, what is the purpose of detector? It keeps only the Doppler component along with the range parameter. Okay, only whatever the change we have observed in the received signal that will be kept at the output, and remaining transmitted component will be eliminated. So the detected signal V1D is equal to sine plus or minus 2 pi f dt from the first signal, actually fd1, but I told you fd1 equal to fd2 equal to fd, minus 4 pi f1 r naught by c, and similarly v2d is equal to sine less or minus 2 pi f dt minus 4 pi f2 r naught by c. This is the only difference between these two detected signals. Now, when you apply these two signals to a phase detector to obtain the phase difference between these two, the phase difference of V1D and V2D is, what is the phase difference between these two? Phase difference between this one and this one. So 2 pi f dt, 2 pi f dt gets cancelled, and what else we have? So delta phi is equal to 4 pi f2 minus f1, f2 minus f1, because this is minus this one, first one minus second one, second becomes positive, so f2 minus f1, remaining parameters are common, we can take common them, and this is the equation. Okay, so we can still further reduce it as f2 minus f1, we can take it as delta phi, delta f. So assume delta f is equal to the difference between the frequencies f2 and f1. So delta phi is equal to 4 pi delta f r naught by c. Okay, so what we need finally, range. So range to the target r naught is equal to c delta phi by 4 pi delta f. Okay, now to make R naught measurement to be maximum, generally we are expecting the radars to get information from the maximum distances. So that's why to get R naught maximum, R naught to be maximum, to make R naught to be maximum, because we are expecting the radar systems to get maximum target information, maximum distance target information, so we are expecting the R naught to be maximum. So R naught to be maximum, what the parameter we need to concentrate on? Delta f. Delta f should be minimum. Okay, otherwise we can say delta phi should be maximum. The phase difference delta phi should be maximum, because both are in proportional to each other. R is proportional to delta f. So if delta phi increases, R also increases. But there is a limitation that delta phi cannot increase more than 2 pi radians. But there is a limitation for whom? For delta phi. It should not increase than 2 pi radians. Okay, so if it increases more than 2 pi radians, then the target becomes unambiguous range. Okay, I told you already, if the information is beyond this first cycle, if the echo is received after the first cycle, then the target echo will be in an ambiguous range. So to make the target information in unambiguous range, it should be 2 pi radians. It should be in 2 pi radians. So 2 pi should not be exceeded by the delta phi. So the unambiguous range is equal to, if you keep delta phi, unambiguous range is obtained by taking delta phi is equal to 2 pi radians. So what is the maximum distance that we can measure using this method? C into 2 pi by 4 pi delta f, that is equal to 2 pi c by 2 delta f. This is the maximum unambiguous range. We can calculate using this multiple frequency CW radar. Okay, I hope you understand. It is very simple. Just instead of taking single frequency, we are taking two different frequencies, f1 and f2, from the same transmitting section, and in the return we are calculating what is the amount of the frequency difference as well as the time difference we are taken. That means after some time we are taking the signal. So if we do some manipulation, like after application of the signal to the detector, what happens after that? We are taking the phase difference between the two received signals, so that we can calculate the range. But it is having a limitation due to ambiguity. So unambiguous range should not exceed. That's why it is the delta phi should be 2 pi. That's why the maximum ambiguous range should be only c by 2 delta f. Thank you.